Oh, there are usually 8 people. Maybe I'll wait 1 more minute before getting started. Are there any questions in the meanwhile? Okay, so today we are going to, 1 second, here we go, discuss Laplace transforms. And unfortunately, all that this is going to amount to from a problem-solving perspective is that it's going to be another way to solve constant coefficients linear equations in which the inhomogeneous part is of the form polynomials, exponentials, sines, and cosines. Right. So we are not like going to learn how to solve a different class of equations, but the theory of these is pretty interesting. And we can see why it won't let us solve new equations once we've covered the theory. So the Laplace transform then of a function f, where let me write, suppose f is defined for t is greater than or equal to 0. And I'm going to have my functions parameterized by time. Then the Laplace transform of f is a function such that if we evaluate that function at s, then that's equal to the integral from 0 to infinity of e to the minus ts f of t dt. And the first observation is that L is linear, and hence an operator. And what this means is that L of, let's say, f plus lambda g, where lambda is some number, well, this is a function such that at s, it's integral 0 to infinity e to the minus ts, and then we have f plus lambda g dt. And that's just the integral from 0 to infinity e to the minus ts of f of t dt plus lambda integral 0 to infinity e to the minus ts g of t dt, which gives us the Laplace transform of f plus lambda, the Laplace transform of g. Now, the second observation is going to be, when does this integral converge? It's an improper integral, so sometimes it's going to diverge. And the observation is if L of f of, let's say, a naughts exists, converges, then L of f of a or s converges for s is greater than a naught. And the reason is that how can this sum fail to converge? We're assuming continuity. And when I say assuming continuity, I mean assuming piecewise continuity. However, in all of my proofs, I'm going to assume continuity, and the proofs have to be modified if you want to make it piecewise. The reason is that this integral does not converge exactly when there's infinite area. And when I say infinite area, I mean infinite absolute area. So for example, if the function is oscillating and there's the area seems to cancel out, but it goes up and down and up and down, and the total amount of area in an unsigned way is infinite. When there is infinite area under the curve, i.e. When the limits as let's say x goes to infinity of the integral from 0 to x e to the minus st times the absolute value of f of t dt is infinity. Because if it converges conditionally, then the limits won't exist because it'll oscillate between points. So this is a result from calculus. But by changing e to the minus t a naught to e to the minus t s for s is greater than a naught, what happens is we effectively divide the integral by e to the at. We divide by e to the let's say s minus a naught. And on t is greater than or equal to, well, I guess that's a separate statement. On t is greater than or equal to 0, this is greater than 1. So this helps convergence. So in general, then, when is the Laplace transform going to exist at all? Because we see that it's going to start existing at some point, maybe, and then it's going to continue existing if it starts existing at some point. Well, so when does L of f converge at all? And the answer is if f has exponential order. And what that means is that if we take, let's say, the limits of f of t divided by some exponential e to the at, we take the limits as t goes to infinity. This is equal to 0 for some value of a. So, for example, e to the at is of exponential order. For any a. As limits of e to the at divided by e to the bt is equal to 0 as t goes to infinity if b is greater than a, right? So an exponential e to the at grows slower than some other exponential when the order is higher. Can anyone think of a function that's not of exponential order?
So it's like even it increases more rapidly than any exponential order?
Yes.
X to the X.
X to the X. Well, if we consider what X to the X is, then that's equal to e to the logarithm of X times X, right? And that's a good example, because if you sort of take logarithm of X is eventually going to be bigger than any B, right? However, I have a simpler example. What about e to the t squared? I'm going to replace all of the x's with t's. Also, because I've decided to t to the t is log t of t. E to the t squared also is thought of exponential order. And that's because you're multiplying by t here, whereas here you're multiplying by log t. The point is that this number, log t or t, they're bigger than any constant eventually, right? So both of these examples work. And the reason is that if you sort of take e to the log t divided by e to the at, then that's equal to e to the log t minus a t. And this gets big. For large values of t. So it's not going to converge to zero. It's going to grow faster than any exponential, even when you divide it by any exponential. I think in the homework, for example, we had a differential equation in which the inhomogeneous part was e to the t squared. And we can't even take the Laplace transform of that. So if your inhomogeneous part looks like e to the t squared, then this technique does not work. And for various other reasons, we're going to see that this technique isn't going to work when the inhomogeneous part isn't of the form a polynomial times an exponential with sines and cosines maybe added in. It can handle exponential times sine times a polynomial. So it's not hard to grow faster than any exponential. In fact, it's not hard to grow faster than any exponential to a polynomial. You make it an exponential to an exponential. So like e to the x grows faster than e to any polynomial, which is even worse, can't be captured by exponential order. This is sort of like even worse. So all of these look like exponentials, but they're not exponentials. They're exponentials composed with other functions, and then they grow quicker than just an exponential. So now let's do some examples of Laplace transforms, and all of these examples are very important. We did last time, we did exactly one example. What is the Laplace transform of just the constant function 1? Well, at s, this is going to be the integral from 0 to infinity of just e to the minus ts dt. And the antiderivative of this expression here is minus 1 over s e to the minus ts, and we're going to evaluate this from 0 to infinity. And what's going to happen is that when we plug in infinity for s, for t, then if s is greater than 0, then this is going to be e to the negative infinity. And that's good because that goes to 0. If if s on the other hand is negative, then this is going to go to infinity. So this is equal to, I guess, 0 minus, then if we plug in 0, then we're going to get e to the 0. So minus 1 over s, which is equal to 1 over s, for s is strictly greater than 0. If s is 0, then well, it's sort of discontinuous if s is 0. So we're going to omit the case. We're not going to consider s equals 0. We're going to consider, we want a continuous Laplace transform. Technically, this integral does, I guess if s is 0, no, then we're integrating 1 from 0 to infinity, and that does not have a finite area. This only applies when s is non-zero, because otherwise we have 1 over s. If s is 0, then we're integrating 1. And that obviously doesn't converge because there's an infinite amount of area under the constant curve of area 1. So this Laplace transform will exist for s is greater than 0, and sort of this matches the pattern that we observed. Because what happens is basically we're taking a function and then we're dividing it by an exponential. And then we want to take the area from 0 to infinity. And at some point, if the function is of an exponential order, there's going to be some exponential big enough such that if you divide by that big enough exponential, the area becomes finite. But if it's something like e to the t squared, then no matter what exponential you divide it by, there's going to be an infinite amount of area. Okay, so the next simplest example is actually going to be, well, what happens if we take the Laplace transform of an exponential? This is actually simpler than the case of a polynomial by a very far margin. And the reason is that all that we're going to get is a product of 2 exponentials here. And so that's the integral from 0 to infinity of just e to the, let's write minus, then let's write s minus a of t dt. And it's going to be the same thing as before, except it's going to be shifted. So we're going to get minus 1 over s minus a from 0 to infinity, sorry, e to the minus s minus a t from 0 to infinity. And this is going to give us minus this expression. So 1 over s minus a. And this is going to happen when this exponent is, well, when this expression is positive, so that this overall thing is negative. So this is positive when s is greater than a. So the Laplace transform doesn't have to exist for all positive values of s. If we sort of have a positive here, that it's going to exist only past a certain positive value, and if a is negative, then in fact we can sort of extend it backwards, because we can even multiply by an exponential and we'll still have finite area because we're already dividing by an exponential. Now, the next cool thing that you can do is you can not just consider a exponential in which a is real, you can consider an exponential in which a is actually complex. And the antiderivative is the same. So really, we are doing the same integral 3 times in these 3 examples. So we are going to write this as the integral from 0 to infinity of e to the minus, and then we're going to write s minus alpha I minus alpha minus beta I. T, 1 second. And so that's going to give us the antiderivative of 1 minus 1 over S minus alpha minus I beta to this expression. And just the question is, when is this going to converge? Well, what happens is that the I beta part, that's just going to be a complex number on the unit circle, right? So the I beta part does not affect convergence at all, because this is basically a point on the unit circle. The I beta is just, so I'm going to write, I guess, my teleportation thing. And then I'm going to do some side remarks that e to the minus I beta is equal to, so cosine of, let's put a t here, of beta t minus I sine beta t is on the unit circle. In the complex plane. And then we're multiplying this by an exponential. And so in the limits, t goes to infinity, this will exist if this exponential goes to 0. And if this exponential does not go to 0, let's say s equals alpha. If s equals alpha, then it's going to oscillate on the unit circle and it's not going to have a limit because it doesn't go anywhere. It just keeps circling around. If s minus alpha is greater than 0, if it's less than 0, then it's going to spiral outwards. But if it's greater than 0, then it's going to spiral inwards to 0, and then it's going to make sense to take the limit at infinity. Once s minus alpha is greater than 0 in order for limits t goes to infinity to converge. So the complex part does not affect convergence at all. And what we get as a result is that this is just the positive thing. And this is for s is greater than alpha. Cool. Well, let's do some other interesting things. What about the Laplace transform of a function? Like, let's do sine first. Let's say sine of beta t. Well, how can I write sine in terms of complex exponentials?
You could do like e to the oh yeah, alpha. So any alpha plus beta. So you would just do e to the IB and then you subtract minus e to the minus e to the minus IB. T.
Yes. And what do we have to divide by?
2.
Except for the fact that we're taking the sine part and the sine part is imaginary, right? So we're going to combine the imaginary parts and we want something real. So it actually has to be 2i. And so the reason that this formula holds is because we basically have cosine, let's write cos beta t plus I sine beta t. Let's S beta t. And then you're from this subtracting cosine, because cosine is even, so it's not affected, and then minus I sine beta t. So overall, you're going to get 2I sine beta t, and then you want to divide by 2I to just get sine beta t. Well, the Laplace transform is linear, so this is 1 over 2I. Then here we're going to get 1 over S minus I beta. And here we're going to get minus 1 over S plus I beta. And so that combines. When we multiply this, it's sort of the opposites of difference of squares. What's the common denominator going to be?
S squared plus B squared.
Yep. And then the numerator is going to be here, we're going to cross multiply. So here we're going to get S plus I beta. And then here we're going to get minus S minus I beta. And you can see that we're going to get 2 times I beta divided by 2I. So it's just going to be beta divided by S squared plus beta squared. And then, okay, I'm not going to do the spoiler yet. You're basically at some point in this lecture going to see what problem solving looks like using Laplace transforms. So I think this is a bit suggestive. Where have you seen things like this before? And like this? Well, I won't say it yet. So let's do cosine of beta t. So this is similar. Except for the fact that we're doing plus, and since it's the real part, we're just dividing by 2.
And this is for S greater than 0.
Yeah, so this holds good for S greater than 0. Because of the previous thing. We saw that's, yeah. And so we can just write this as 1/2. And then these are going to be the same integrals, except there's going to be a plus sign. So the cross multiplying gives us the same S squared plus beta squared. And then we have S plus I beta plus S minus I beta. So that gives us 2S, and then we divide by 2. So that just gives us S over S squared plus beta squared. So we're covering our bases. We have constant over quadratic irreducible because beta squared is positive, and linear over irreducible quadratic. And then we have 1 over linear factors. So that's a spoiler as to what problem solving is going to look like. Basically, okay, I'll just say it. When you do partial fractions decompositions, partial fractions split into linear terms. And then they also split into irreducible quadratics. And then when in the reducible quadratic case, you have constant and polynomial and linear. So we're getting all of the pieces of what would give us partial fractions decompositions. So this was a section of like very important examples that are going to be super relevant. But I'm just now going to do like an example of applying these things. Let's suppose f of t equal something like 2 plus 5 e to the minus 2t minus 3 sine to the 4t. And so if we compute the Laplace transform of f, that's going to be twice the Laplace transform of 1 plus 5 times the Laplace transform e to the minus 2t minus 3 times the Laplace transform of sine to the 4t. And then we know what all of these are. So on the homework for these elementary Laplace transforms, we already have the formulas, and so we know what this is going to be. This is going to be a function of s. I don't have to write that it's a function of s. That's sort of implicit. So sort of the left-hand side is going to have an implicit s here. But on the right-hand side, in terms of s, what is the Laplace transform of 1? Let's see if we remember this.
1 over s.
Yep. And then here, we're going to get 5 over what's?
One over s plus 2.
Yeah. So I was seeing if you'd remember the shifts. And then like sine or cosine, I actually don't remember which one is which. So let's look that up. Yeah, so the shift when you have an exponential, it goes in the opposite direction. If you have at, then it's s minus a. Sine is the one that's linear. And that's sort of better. So sine is in general a better function. It's locally linear at 0. Its derivative is cosine, which doesn't have a negative sign. And also it has the nicer Laplace transform. So sine is the one that's nicer, except its integral has a negative sign. So minus 3. And then because it's the constant, not the linear one, it's going to be 3 times 4. So minus 12 divided by s squared plus 16. And I'm not going to simplify this. You can bring this to a common denominator. Later on, we are going to be bringing these to common denominators all of the time. So basically, if you have the expressions like this, it's easy to take the Laplace transform once you have all of the formulas in mind. But we're going to find out that there's actually a bunch of other cool things that we can do. So I called this observation 2b for second observation. So I guess third observation, since I'm apparently writing it out in words. What color did I use to underline those? It was blue. So let's take the derivative of the Laplace transform. And it's going to be the nth order derivative with respect to s of the Laplace transform of f. So what this is equal to is it's the derivative, sorry, s to the n. Of the integral. This is an integral with respect to t. Now, assuming that the function is like not very badly behaved. So it's basically a theorem that you can change the derivative and the integral. If the bounds of the integral don't depend on s, then you can bring s inside of the integral. But inside of the integral, there are sort of like two variables. There's s and t. So what do I mean by the derivative with respect to s? I mean the partial derivative. So this is equal to the integral from 0 to infinity of partial with respect to s. This is just to make it clear that s and t are non-interacting. They're separate variables, and we're taking the s derivative. So no chain rule for t. And so if we see this, then it's clear that the only term which has s dependence is this term. And now what happens when we take the first derivative? Well, it's with respect to s, so we multiply by negative t, right? And so in general, we see that this is going to be negative t to the power of n, e to the minus st of f of t dt. And we can rearrange this as saying, let's bring out the -1 to the n out front of the integral. And then we're going to get the integral from 0 to infinity of e to the minus st times t to the n f of t dt. Well, I just made it worse. So what's the corollary? The corollary is, well, actually, let's just rewrite this. This is equal to the Laplace transform, and well, rather -1 to the n, times the Laplace transform of t to the n. That does not look like a t. So as a corollary, if we are transforming some polynomial times a function, then what that does to the Laplace derivative, what that does to the Laplace transform, is that it differentiates it and multiplies it by -1 to the n. So this is a good formula. This is a very useful and important formula. Let's look at one corollary of this fact. What happens if we're just differentiating, what happens if we just transform t to the n? And by the way, we're taking away, when we're doing this, an integer number of powers of t, because n here is a natural number. And the natural numbers have 0 in them, by the way. The 0 derivative, it just says the Laplace transform of f is f, as the Laplace transform of f. So this doesn't make sense for example, for fractional numbers or for general real numbers. And we can talk about what happens in that case later. So what happens if we have t to the power of n for n is a natural number? Well, we can just transform this in terms of the Laplace transform of 1. So it's going to be -1 to the n times, well, I guess I can just write okay, I'll write it out in full. Dn ds to the n of the Laplace transform of 1, which is going to equal -1 to the n times the function 1 over s, and then we're taking the nth derivative of this, right? So by the way, let's just see how this behaves. So if we take 1 over s and we sort of take the 0th derivative of it, then it's just 1 over s. 0th derivative. If we take the first derivative, then what happens is this is the power of -1, so we multiply by -1. And then we get s becomes s squared. What happens if we take the second derivative of this? Well, now after multiplying by -1, we're also going to multiply by -2. And then it's going to become s cubed. And so if we take the third derivative, then it's going to be -1 times -2 times -3, 1 over s to the 4th. So in general, what's the nth derivative going to be of 1 over s?
-1 to the n times n factorial over s to the n.
S, well, look, if it's 0, then it's 1. If it's 1, then it's 2. So s to the
n?
If it's 0, then it's 1. If it's 1, then it's 2. So n plus 1. Okay. But so this -1 to the n cancels with this -1 to the n. And what we get as a result is that it's going to be n factorial divided by s to the n plus 1. And this is, again, for n is a natural number, which is 0, 1, 2, etc. In case you're wondering, yes, the natural numbers contain 0. That is the objectively correct answer to that question. Some people who do analysis disagree because they don't like all of their indexing to be n plus 1 because of divide by 0 errors. But if you do logic, I basically do logic, then the natural numbers, of course, start at 0. It's preposterous to suggest otherwise. Okay, so let's just do you know what? Let's do observation 2 and then let's do examples. So 4th observation. This observation is arguably simpler than the observation that we had before. So what happens if we take the Laplace transform of e to the at times f? So we basically saw this exact behavior when we went from the Laplace transform of 1 to the Laplace transform of e to the at. The same thing is going to happen. This is the integral from 0 to infinity of e to the minus st. This is as a function of s. Actually, I'm going to want to make that s dependence clear in order to make this formula comprehensible. Times e to the at times f of t dt, which is the same as the integral from 0 to infinity of e to the minus s minus a t of f of t dt. And what's this equal to? This is the Laplace transform of f evaluated at what?
S minus a.
Yeah. So this, by the way, sort of looks like the exponential shift theorem, except it's even better. Because we don't get an e to the at out front. So it's sort of like the exponential shift theorem had this substitution, and then it had an e to the at out front. But here we don't have this. So this sort of is reminiscent of the exponential shift theorem. But that was for polynomial operators, not all operators. We see that this is a different operator, and we don't get we get a different version of the exponential shift theorem. And then I have some examples. I'm going to do, I guess, the easy example and then take a break and then do the harder example. Okay. So let's say we want to take the Laplace transform of e to the minus 2t times sine of 4t. Then let's sort of make the S dependence clear, although we don't necessarily have to. Well, by the previous results, this is going to be the Laplace transform of sine of 4t, evaluated at what?
Is that possible that S plus 2?
Yeah, S plus 2, exactly. In general, all of these exponents the sign gets flipped. And we know what the Laplace transform of sine is. Remember, sine was the one that was better than cosine. So we're going to get sort of beta up top. So it's going to be 4 divided by S squared, except we're now substituting S plus 2 for S. Plus beta squared, so 16. And by the way, so I'm going to allude to sort of like a very important thing. This expression right here, what does it look like? It looks like a sum of 2 squares, right? This is a sum of 2 squares. However, if we sort of expand this out, we get S squared plus 2S. And then we're going to get 16 plus 4 plus 20, right? And so just recall,
4S?
by the way.
4S?
Why is 2S? It should be
4S,
4.
thank you. Yeah. So let's recall, by the way, what happens if you have 1 divided by a polynomial? If we have, so I guess this is a side. If we have, let's say anything, f divided by ax squared plus bx plus c. Then what does this look like? This is relevant for partial fractions decompositions. So there are going to be 2 cases if these are real coefficients, and they depend on I guess 3 cases. They depend on which quantity. Delta equals what? So it's the discriminants. What is the discriminants of a polynomial?
B squared minus 4AC.
Yeah. So if delta is greater than 0, then we can complete the square. Remember that? completing the square. So if delta is greater, so if b squared minus 4ac is so in general, if I sort of have I guess let's factor a out of everything. So I'm going to have a x squared plus b over a x plus c over a. And then if I have an expression of the form x plus, let's say, alpha squared, then that's going to equal x squared plus 2 alpha x plus alpha squared, right? So we want b over a equal to 2 alpha, right? So what's going to happen then is that this expression here is going to become a times x plus alpha, x plus b over 2a squared. And then we get b squared over 4a squared, right? And we've added that. So in general, we're going to get c over a minus b squared over 4a squared. And then I guess the a is out front, so you can also write this as a by x plus b over 2a squared, and then plus c minus b squared divided by 4a. And now we see where sort of the relevance of the discriminant is. So this is related to the discriminant. This is basically negative the discriminants. Divided by 4a. I do not like that it's negative. Right. I do like that it's negative. So if b squared minus 4ac is greater than 0 or greater than or equal to 0, then we get roots, right? Then this has roots. If the discriminant is less than 0, then it's impossible to have roots, right? So if b squared minus 4ac is greater than or equal to 0, then we factor. So there are two cases. If delta is greater than or equal to 0, we can factor via the quadratic equation. However, if the discriminant is less than 0, then there are no real roots. And the reason that there are no real roots is because this quantity is greater than 0 if delta is greater than 0. Okay, here's the deal. If a is negative, then it's going to be minus a sum of 2 squares. So it's actually better to have a out front. I guess I can do the analysis here instead. You know what? I'm going to erase the line where I put a out front. Because the sign is going to be misleading. Basically, it's going to be a times, and then it's impossible to factor this if we have a sum of two squares here. So what this quantity right here is that it's, well, if we sort of take c and then we multiply by 4a squared. So it's negative the discriminant divided by 4a squared. And 4a squared is going to be, well, if it's a quadratic, then a better be non-zero, and a squared is then going to be strictly positive. So this is greater than 0 if and only if delta is less than 0. And if delta is less than 0, then we get a sum of squares. Which shows that it's impossible to factor over the real numbers, because the expression x squared plus a squared has no solutions, because x squared is always going to be positive, and then a squared is going to be strictly positive for a is non-zero, which we're assuming that delta is strictly less than 0. And so this is very important when doing partial fractions, because when you're doing partial fractions, you might encounter an expression like this. Let's say you have this. And then the question is, so how do I partial fractions decompose this? Well, I calculate what the discriminant of this polynomial is. And if the discriminant is negative, then I know that I'm going to be able to complete the square. And then when I complete the square, when you're computing the Laplace transform, or when you're computing the inverse Laplace transform, more pertinently, when we're doing this backwards, then you're going to shift, and then it's going to become of the form x squared plus a squared. And then when it's of the form x squared plus a squared, we know that it's either going to be sine or cosine, depending on what the denominator is, right? So that's just a preview of what's about to come. But I thought I'd do a digression about completing the square, because completing the square is going to be an important skill, because we're going to be doing partial fractions today. That's basically what the lesson is about. So it's 7:02. Let's do a 13-minute break. So that means 7:15. See you then. Okay, so we did one example. And this was shifting by an exponential, but now let's do an example where we shift by a polynomial. And I actually chose to do the annoying example as opposed to the nice example. So let's do the Laplace transform of t squared times cosine 3t. So what happens here is that this is t squared. So it's going to be -1 to the power of 2. So that vanishes. D squared ds squared of the Laplace transform of cosine of 3t. Now, cosine is the one that's actually more annoying than sine. If I did sine, it would be easier to take this derivative. So this is d squared ds squared. Of so it's going to be s divided by s squared plus 9. And if we want to compute the second derivative, first we compute the first derivative. And I always tell my calculus students to not memorize the quotient rule because it just follows from the product rule. But whatever, let's do the quotient rule. So your sort of differentiation is more important. So you're differentiating the top and multiplying by the bottom, and then it's negative. So it's going to be the derivative of s times s squared plus 9 minus the derivative of s squared plus 9, which is 2s, times the top, s squared. And then the bottom becomes squared. So this is 9 minus s squared. Then we use quotient rule again. So the derivative of the top is minus 2s times s squared plus 9 squared. And then if we take the derivative of this, we're going to get 2 times this times the derivative of this. So that's going to be 2s times 2, so 4s, and then we're subtracting because it's the second term. So minus 4s s squared plus 9 first power times the derivative, sorry, not times the derivative of this, just times the top. There's clearly a common factor of s squared plus 9, which we're going to get rid of. So at the moment, the denominator is s squared plus 9 to the 4th power, because we squared the denominator when we did quotient rule. And so if we simplify that, s squared plus 9 cancels out, and the 2s we can take out front. Then here there's an s squared plus 9. I'm going to just make that negative. And then here there's minus 2. So it's going to be plus 2s squared minus 18. And then the denominator, because we already took one of the s squared plus 9s out, is s squared plus 9 cubed. And so what we get here is am I? Yeah, fine. Yes. 2s times s squared minus 18. Okay, That way, by the way, was slightly more annoying than had we done it differently. So I don't have the second approach in my notes, but let's do this second approach. So first off, when we did the Laplace transform of cosine and sine, we actually did not do it in the most efficient way possible. So we wrote, for example, cosine as being the sum of two complex exponentials, right? Divided by 2. But there's another way to write cosine. Cosine is also just the real part of e to the it. In this case, e to the, so cosine of 3t is equal to the real part of e to the 3 a plus I beta. I guess I3t is how I'd write it. Or 3ti, I'm not sure. How have I been writing it usually? So the catch is then that t squared is a real function, right? So the Laplace transform of t squared cosine 3t is equal to the Laplace transform, and then I can bring t squared inside of the real part. You know what? I think it's actually 3it. That's the best way to write it. Is it? What have I been writing? I guess when it's a number, it's sort of different than it's a variable, although the number is sort of a coefficient. I beta t. Okay, you know what? Fine, let's just keep the I out, friends. Sure. This matters so little. But the catch is that basically the Laplace transform is if you take f, then this is equal to integral from 0 to infinity of e to the minus ts, which is entirely real. For s is a real number. For s is a real number. This is entirely real. And at the moment, we're just going to be evaluating the Laplace transform on real numbers. If we evaluate the Laplace transform on complex numbers, then this doesn't apply. And by the way, it does make sense to evaluate the Laplace transform on complex numbers sometimes. So for s real, and if we take the real part of this, then does it commute with integration? Yes, it does, because an integral is just like a sum. And if you're summing a bunch of things and taking the real part of that, it's the same as taking the real parts of the things and then summing them. Then this part is just real if s is real. So that's equal to the integral from 0 to infinity of, and then we can just commute everything through. And then we get the real part of f of t, which is equal to the Laplace transform of the real part of f. So the lesson then is that we, if our value of s is real, and it is in this case, then we can just commute the real part outside. And we get just the real parts of the Laplace transform of t squared e to the I 3t, right? And so taking the second derivative was a bit annoying because we had to use quotient rule twice. What's easier is that we do know how to take the Laplace transform of a t to the power of n. Because we have a formula for that. Because here, doing the iterated derivative did not require quotient rule. It was pretty direct, right? So it's better to get rid of the exponential and then apply this rule. So if we're evaluating this, I guess, on S implicitly, then this is going to be the real part of the Laplace transform of e to the I3t. I can put the S aside here. Sorry, e to the t squared. So its sign changes, it's S minus 3. And the Laplace transform of t squared is going to be, so for all of these, it's going to be n factorial divided by s to the n plus 1, no signs, so that's nice. So it's going to be 2 divided by t cubed. Oh, sorry. It's shifting by 3i. I was wondering, that was looking like it's a very real. So it's shifting by s minus 3i. So that's the real part of 2 divided by s minus 3i. To the third power. And so that looked like an easier calculation. But for the sake of time, because this is sort of a not reduced, right? And for the sake of time, I mean, in order so that I have a 3-hour lecture, so to pad things out, let's actually see how this expression reduces to that expression, because this is sort of an unacceptable final answer. And then I guess what we're going to see is that the amount of work is going to be basically the same. It's not actually going to simplify things. Or is it? Or is it? That's the question. So S is a real number. So what we can do instead is we can multiply it by the conjugate of this, right? So that's the same as the real parts of 2. And at the bottom, we're going to get s squared plus 9 cubed. And then what do I have to put at the top?
S plus 3i cubed.
Yep, good. And actually, this is good. So we're going to do binomial theorem on this. Now, the thing is that half of the terms are going to be imaginary, right? So I guess I don't even necessarily have to write those terms out. But let's do it for just to pad things out. So if I have s plus 3i cubed, that's equal to, so we have binomial coefficients. So we have 3 choose 1 is, well, 3. I guess 3 choose 0 is 1. 3 choose 1 is 3. And then remember Pascal's triangle? So for 3s, it's just, yeah, they're symmetric. I didn't really have to write out Pascal's triangle for this. So what we're going to get is s squared, then plus 3s squared times 3i, right? Plus 3s times 3i squared. Then plus 3i cubed, right? And so if we take the real part of this, then this is going to be real. And this is going to be real, right? So we're going to get s squared. So it's going to be 27 s. Minus. So I squared is -1. So minus 27. That's bad. That is bad. Because here we got, oh, here I didn't know how to calculate. 9 minus 18 is not 18, it's 27. Good. However, there was a 2. Where did the 2 come from? Oh, the 2 comes from here. Good. So actually I forgot about the 2. Which I can factor as 2s s squared minus 27. And you know what? This binary expansion, it's just like very routine if you know the binomial theorem. I wrote it out in full, but you can do it in much quicker if you're just looking for these 2 terms. And this was actually the better approach. This approach was shorter. We had to do a long discussion about taking real parts. In fact, we could have just taken the real parts of this thing when we calculated the Laplace transforms of cosine and sine, but it was a bit easier to present it there, and I was intending to present it differently here. So the second approach, this is easier. Second approach is better. Do you know why the second approach is better? Let's imagine that we were taking like a higher order derivative. Then doing quotient rule more than 3 times or more than 2 times is super painful. And binomial expanding, well, that's easy. You just do binomial coefficients. So you can just write it out formulaically. Even if you're trying to binomial expand something to the 10th power, that's not bad, actually. You can just do that because you just use the formula. But if you're trying to take quotient rule derivative of something n times, then no, that's too hard. That's you're going to mess up. So the second approach is clearly better. Particularly when we have like t to the n cosine beta x for, let's say n is greater than or equal to 3. Okay, and now here we get to, so what observation are we on? So now I'm going to explain why the Laplace transform is actually useful. You don't know why it's useful yet. This is why the Laplace transform exists. It's this fact alone. So let's take the Laplace transform of the derivative of f. What that's equal to is that's the integral from 0 to infinity of e to the minus ts times f prime of t dt. Now, what does this look like? What are we going to do?
Product rule.
Which
Yeah.
product rule, when you integrate it, is called integration what?
By parts.
Yes. So usually I'd write f and dg, but I have f here, so that's bad. So I'm going to call it u. U is e to the minus ts, and dv is equal to f prime of t dt. So what is du? This is as a function of t, because remember, we're integrating with respect to t.
then it's minus e to the minus ds.
I mean, did we get a prefactor when we differentiate? What's the prefactor? Minus what?
Oh, minus s, not minus d.
Yes, minus s. And then when we integrate this, well, it doesn't matter what constant we choose, so it's just going to be f. And the reason that it doesn't matter what constant we choose is because how does integration of parts work when there are bounds? That's the question, right? And how integration of parts works when there are bounds is that you write the cross term. And you evaluate the cross term on the bounds. So for example, if we changed f of t to f of t plus c, that would disappear when we did this evaluation. Yeah, so this is how integration, now we get minus this. However, there's a minus sign here. So it's going to be plus integral. But look at this. S is constant with respect to t, right? So we can just take it outside of the integral. Now, the hypothesis is going to be sort of, we're taking this where, so this is going to converge if f grows strictly slower than this exponential, right? So first off, this is going to make sense where the Laplace transform of f and where the Laplace transform of f prime makes sense. So suppose both L of f and L of f prime makes sense at S, or rather converge. So this is going to be valid when both Laplace transforms are defined. Because here we're going to get the Laplace transform of f. So the formula, they're just going to be undefined terms unless both of them converge, right? Okay, well, if we're in the domain where the Laplace transform of f makes sense, then the catch is that this is going to be something which goes to 0 as t goes to infinity. That has to happen for the Laplace transforms to make sense. I guess that you can integrate a function like 1 over x squared. But then let's suppose that we just move past that point a bit and then it gets, anyway. So make it strictly bigger than the minimal point if there is a minimal point, but if there's no minimal point, then we're good. And there it won't be in general a minimal point. Anyway, boring details. The point is that the infinity thing goes away and then we're going to get minus f of 0. And then this is going to be s times the Laplace transform of f. And how we're going to write this is we're just going to switch the order of the terms. You'll see why in a second. So the amazing thing about the Laplace transform is that calculating Laplace transforms of an unknown function, if you're differentiating the function, then you just multiply by s and subtract a term. So in particular, if we have a differential equation that has powers of an unknown function y, and we take the Laplace transform of it, then we're going to get an equation for what the Laplace transform of the unknown function y that solves the differential equation is. And then we can solve it. And then we can invert the Laplace transform, and then we solve the differential equation. So that's how it's going to work. That's the game. Let's look at a corollary of this. So what I said right now, in very quickly, that was spoilers. We're going to see that in full detail in a second. So what happens, for example, if you take the Laplace transform of the second derivative of f? Well, applying this formula, it's going to be s times the Laplace transform of f prime minus f prime of 0. And this is going to be s squared, L of f. And then we still have an s, so it's going to be minus s f of naught minus f prime naught. And so in general, what the pattern is, and you can sort of see this, is that if you take the Laplace transform of the nth derivative of f, then that's going to equal to s to the power of n times the Laplace transform of f. Then the last term that we're going to get is the undifferentiated term, and the powers are going to go down. See, this is s squared s to the power of 0. So it's going to be minus s to the power of n minus 1. The signs don't change, it's always minus, times f naught minus s to the n minus 2, if that exists, times f prime naught, and then minus all the way down to the last term is going to be the n minus first derivative. See, if it's the second derivative, it's going to be the first derivative. So it's going to be the n minus first derivative. Okay, so now I'm going to talk about the thing that I haven't talked about all semester and that everyone exclusively spends the semester talking about. And that's the notion of an initial value problem. I've never talked about this before, which is ridiculous, because almost every single homework problem in most differential equations courses is an initial value problem. So the idea is this. If you have a nth order ODE, and what does the general nth order ODE look like? It looks like y, the nth derivative, is equal to some function of, let's say t, we're writing it in t in this class, y up to the n minus first derivative. You can't do this if you're writing on paper. If you're running out of space, then you can't just move things over until you make enough space. Right? If you have an nth order ODE, the general solution is going to have n parameters. And we definitely saw this with linear differential equations, for example, but it's generally true. The solution is going to have n parameters. So if we want a unique solution, so not a general solution, but a unique solution, we should give n equations. Now, in general, if you have n equations and n unknowns, you might have like an integer number of solutions. For example, if you take the intersection of a circle and a line, you might have two solutions. A line might intersect the circle twice, right? So how do we ensure that there's a unique solution? So this is this idea that we want n constraints is the moral idea. And so like idea one is that maybe you can say something like f of like y of 0 is let's say a, y of 1 is equal to b up to y of n minus 1 is equal to alpha n, where that's the nth letter of the alphabet. However, this is sort of like, this is not a good set of n equations. So you might have multiple solutions. In fact, what happens is you might even, some of these equations might even be redundant, depending on what the algebra is. So it's possible that you might even have a space of solutions. Let's say of dimension greater than 0. If you have like discrete solutions, then it's sort of like a dimension 0 space. But if you sort of have a continuous family of solutions, that it has dimension greater than 0. So this is sort of like a bad set of initial values. So idea 2 is, well, this wouldn't be your idea 2. This is sort of like a stupid thing to propose. What if you give y of 0, let's say alpha 1, and then let's say you give the first derivative at not 0, but at 1. And then you give the n minus first derivative at the point n minus 1. So this is better, but still not perfect. Because there might be multiple solutions. But do you know what will give a unique solution provably without things? So correct idea is to give what?
Everything at 0.
Exactly.
It's a little like a Taylor series.
Yeah. And so now I'm going to argue as to why this gives a unique solution. So there's like a very fundamental reason as to why it gives a unique solution. Yes, in a Taylor series, technically a function is determined if it's analytic by its Taylor series. But in this case, sort of, if we know what the first n derivatives are, we also know what the n plus first derivative is. Or rather, if we know what the first n minus 1 derivatives are, we also know what the nth derivative is because it's given by this differential equation, right? And if you differentiate this, you get the next derivative, right? So if you're using the Taylor series idea, then technically all of the coefficients of this Taylor series are determined by the first n derivatives. In fact, that's a better reason than I had. That's the reason that I'm going to use. Y sub n minus 1 is equal to alpha n. Then y of n is equal to f of t y up to y to the n minus 1. This determines y n of 0. And also, by differentiating, the above, you also get all higher derivatives. Sort of, if you take chain rule, then you're going to get, when you do the chain rule expansion, it's going to be a multivariate chain rule. So it's sort of hard to see. But all of the factors that you get outside from chain rule would be derivatives of y evaluated at 0. And then you can always reduce them to being lower order derivatives because anything above n we have a formula in terms of the other derivatives. Get all higher derivatives. And this is like follows from multivariable chain rule. So we know all of the Taylor coefficients. So at this point, you'd like to say that the function is unique. Because if the Taylor coefficients are determined, then the function is determined, except that's not entirely true. So intuitively, this determines the function. Now, in general, the non-uniqueness of Taylor series, we actually get a stronger thing here. So we can guarantee that it's unique in a way that's even stronger than the Taylor series arguments. But I'm not going to say that it's true for all continuous functions. There might be some very weak assumptions, which are you're never going to encounter a function that violates those assumptions. So like assuming little more. And I'm not a person that does differential equations, so I don't actually remember what the assumptions are off the top of my head. Also probably saw them when taking differential geometry. Because in differential geometry, we actually care about solving differential equations and we care about proving the solutions exist. Assuming little more than continuity of f. Get uniqueness. And this is a math theorem. So you can prove it. Now, the reason that I was going to justify it wasn't actually the Taylor series justification. It's this. Look at this pen. It fell. The point is that in physics, you have differential equations. And if I drop this pen, it's only going to go one way. If you start the system and you start evolving it, it's just going to evolve. Another way that you can see this is computers. Computers can solve differential equations. Computers can sort of do discrete time intervals, and then they can update these things. And sort of because a computer can solve the equation, the solution has to be unique. So you can also do numerical methods that provably approximate the correct solution, or just nature. Nature is deterministic modulo quantum mechanics, but that's because that doesn't operate by differential equations. Although like observing something in state collapse, I don't understand state collapse. It's sort of like not part of the theory. Quantum mechanics is sort of deterministic if you don't have state collapse. Anyway, I took the full quantum sequence in undergrad. Okay, going back to this, like nature evolves in a unique way. So if you give all of the initial conditions, sort of like a physicist would say, well, obviously, if you give conditions like this, it's going to be a unique result. So uniqueness is obvious to physicists. Okay, if you give differential, if the conditions like this, then in fact, you're not going to have like the case of a line intersecting a circle. You're actually going to get exactly one solution, and you can prove this. It's a hard proof. It requires analysis. And so I'm not going to do that proof because you would want to see it. But you can prove it. So the point is that's like giving conditions like this or this isn't ideal. But like this, you get a theorem. So what does this mean? This means that when the most courses on differential equations pose problems like this, they give you the differential equation and then they give you the initial conditions at 0, usually. So is it important that we evaluate it at 0? No, it's not. We can evaluate it at any other point. However, like notice that the Laplace transform that we've been studying this entire time, this integral starts at 0. Why does it start at 0? It starts at 0 because you usually give initial conditions at 0. If it started at a different value, then this theorem about computing the Laplace transform of a derivative, it would not evaluate it at 0 if this integral didn't start at 0. But because the Laplace transform starts at 0, it's suitable for initial conditions at 0. If you had initial conditions at any other points, then you'd have to change your definition of your Laplace transform. So you just give initial conditions at 0. That's sort of the accepted thing. So what does this mean in practice? In practice, if you give an equation and you find the general solution in terms of a bunch of parameters, and then you have these things, then you have n equations and n unknowns. So you would solve every single problem on the homework by doing whatever you did on the homework, and then plugging in numbers, and then solving equations. But plugging in numbers and solving equations is sort of boring. That doesn't have anything to do with differential equations. That has to do with multiplying numbers and algebra. And so I just didn't do it at all. I did not talk about initial value problems in the entire course until now. And the reason that we're going to talk about it now is because we actually get the initial coefficients coming up in the Laplace transform. Well, then why couldn't we do it in terms of variables? Variables would also work. Well, the problem is that then we're going to do partial fractions expansions. And you can't do partial fractions expansions in terms of variables because you might have a quadratic be irreducible or not irreducible. And so you actually need numbers in order to solve this. So this is why I am forced to introduce initial value problems in lecture 10 out of 15 in the course. Okay, so that was this digression. But this is secretly what all of the homework problems would have looked like in any other offering of this course. You'd have to plug in numbers at the end and it would be boring. When you're doing Laplace transforms, though, you don't have to plug in numbers after finding the general solution, because the catch is that the Laplace transform will not find the general solution. It will find a particular solution to a differential equation given initial conditions. So now I can explain why all of this. So I said that I was going to explain why the Laplace transform is useful. And then what I did to explain that was I gave this observation. And then I talked about initial conditions. Now you're going to see why this is useful. So example. So suppose find L of y for y is a solution of I want to write y prime prime plus 2y prime plus 5y is equal to e to the minus t. And this is a second order differential equation. So I'm going to give y and y prime. Second order, therefore, two equations. Y of 0 is going to be 1, and y prime of 0 is going to be minus 3. So assuming that that y satisfies this equation, we can take both sides, the Laplace transform of both sides of this equation. So I don't usually write solution, but I decided to, and I should highlight it in green. So if we take the Laplace transform of y prime prime plus 2y prime plus 5y, well, that's going to be the Laplace transform of these terms individually because it's linear. But the Laplace transform of y prime prime is going to be s squared times the Laplace transform of y, and then we go down. So it's s squared, then minus s, and s is y of 0. And then minus the 0th power y prime of 0. Then it's going to be plus 2. I guess I can maybe fit this all in one line. times the Laplace transform, S times the Laplace transform of Y. Minus Y of 0. I can't fit it all in one line if I just move this over. There. And so I can rearrange this to group all of the Laplace transform terms. So it's going to be S squared plus 2S plus 5 times the Laplace transform of Y. So you always want to group these terms. And then if we just plug in numbers, this is going to be 1. This is going to be -3. And this is going to be 1. So then keeping the S term, it's going to be minus S. And then here we're going to have -3 plus -2. So -5. Oh, wait a second. That's not what I'm getting. Oh, -3. It's -3. There's this minus sign. -3. So that's +3 minus 2 is 1. So see, I when I wrote these bars over the thing, I actually didn't like this because I thought there was a big risk of me getting confused, and there was. In general, you should never cross things out in equation unless you're crossing out two adjacent terms. And then it would be very bad to sort of like, I guess, cross two things out like this because you have a string of equalities and then the previous equality becomes false. So in general, you shouldn't cross things out and replace them with things. You should just write equals to and write another equation. The only case in which crossing things out is permitted is if you have two adjacent terms which literally cancel each other out additively. Then the equation remains true if you cross them out, all parts of the equation. Anyway, so that's what you have here. And then on the other side, we have the Laplace transform. So this is of the right-hand side of e to the minus t. And do we remember what that is? This is in terms of S.
One over S plus 1.
Good. Yeah, the sign changes. And so therefore, we have that S squared plus 2S plus 5 times the Laplace transform of Y is equal to 1 over S plus 1. And then these terms have to get moved over. So plus S minus 1. Okay, bringing it to a common denominator, we get S squared plus S minus S plus 1. Is S squared minus 1 divided by S plus 1. But obviously, sorry, I forgot something. There's this one here. Right? We shouldn't forget this when we're doing this. So it's actually just S squared. This one cancels with this -1, S squared. And so what that implies is that the Laplace transform of Y is going to equal to S squared divided by S plus 1 times s squared plus 2s plus 5. Okay, now we can basically see what problems the Laplace transform lets us solve. So this is a rational function. And if we do partial fractions on that rational function, then we can invert the Laplace transform because we had a bunch of Laplace partial fractions looking things. Let's see what's not going to work. Let's suppose that instead of having constant coefficients, we had something like multiplying by e to the at. So let's say we multiplied one of these by e to the at. Then the problem is that would give us the Laplace transform not at s, but at s shifted over by something, right? And sort of that equation we can't solve, because if we have an unknown function evaluated at s and at s minus a, then there's no general way that we can relate s, an unknown function at s and an unknown function at s minus a. So that's useless. Basically here, it's fine if we have another term, but if we have a term multiplied by y and that term is an exponential, and it's not all the same exponential. And if it was all the same exponential, then you could just divide through by that exponential, you'd be done. If it's there are different exponentials, then you get the Laplace transform shifted over, and you can't solve that equation in general. So that's bad. So this doesn't work. Now, what if you have sort of like a power of t? Well, the power of t isn't actually that bad. Because you get a differential equation for L, and then maybe you can hope to solve it. But let's say you had a second order equation and you had t to the 5th power here. Then you turned your second order differential equation into a 5th order differential equation, so good job. So t is sort of like manageable if it's a single power of t, but if it's a higher power of t, then it's strictly making things worse, right? So that's bad. So realistically, UI, it's constant coefficients. That's the stuff that you can deal with. Now, what about this? What if we had different functions here? Well, sort of t squared is also good, e to the t. If you have times sine, that's good. And the reason that all of this is good is because what these transform into is rational functions. So if we have any of the stuff that we had before, which is like sines, cosines, multiples of t, multiples of sine, multiples of e to the at. So you can even have something like e to the t squared, e to the 3t times sine times cosine. That's not bad. That's actually manageable. And that's going to give you a rational function. So if the Laplace transform, if the inhomogeneous is a rational function, this is going to give you some polynomial stuff. And then you're going to get the Laplace transform. You can solve for it in terms of a rational function. But now let's say that the thing here is not any of the stuff that we had before. Then the Laplace transform might not be a rational function. And then you're going to be able to solve for it, but it's not going to be a rational function. And we won't be able to invert Laplace. So Laplace transform inversion is possible always, as like a math theorem. The Laplace transform has an inverse, but there isn't a nice formula for it. So in other words, we can sort of do it by bits and pieces, but the bits and pieces that we know how to do are sort of the elementary components of the rational functions decomposition. So doing all of this analysis, what have we discovered? We've discovered that if we have a differential equation, then doing the Laplace transform of the equation is going to let us solve the Laplace transform as a rational function. And therefore, and this is the part that I haven't done, therefore, we're going to be able to invert it and actually get a concrete solution, provided that it's a constant coefficients differential equation where the thing here is like literally the same thing that we had that we could solve using the operator power series method. So we haven't learned how to solve any new equations. However, the Laplace transform is very cool. But we're not going to be able to solve new equations that we weren't able to solve before. So sorry to break that to you. But then the question is like, so how would I invert this? And so that's a good question. Oh, it's 8:10. I actually need to write out some examples. Or you know what? I think that I'm going to end half an hour early without writing out more examples. So I'm going to go on for 20 more minutes, if that's okay with people. And then, yeah, so it's sort of like an awkward time to have a break because anyway, sure. Okay, 20 more minutes of lecture and then, well, we're going to end for the day. So now we get to the inverse Laplace transform section. So if we're able to solve for what L of y is, then the question is, are we able to solve for what y is, knowing what L of y is? Well, is the image of Laplace, the Laplace transform, literally every single function? I'm not sure about that. So maybe there are some functions that don't have a Laplace don't have an inverse Laplace transform. However, I can tell you this: L is injective in math speak, meaning that's if f the Laplace transform of f is equal to the Laplace transform of G, then f equals G. And the Laplace transform only looks at the values of these functions on the positive real numbers. So on t is greater than or equal to 0. Of course, that's we have to stipulate because the Laplace transform doesn't see the values of these functions on negative values. But anyway, ignoring that, the point is that thus, if we know that L of y is equal to some function f, and we find some function g with the Laplace transform of g being f, then that implies that g is equal to y. So therefore, if we can find, well, for differentiation, you can ask about the problem of finding the antiderivative. For Laplace transforms, you can ask the problem of doing the anti-Laplace transform, and that's called the inverse Laplace transform. If we can find some function that maps to this function that we discovered here by the Laplace transform, then we know what y is, provably. Any Laplace antiderivative meaning is the unique Laplace antiderivative, is the unique inverse. And so we get a solution to the differential equation satisfying the initial conditions. Okay, that's great. So basically this makes sense. And the notation that we're going to use for this is we're going to basically write L inverse of f. So this will denote, if it exists, any sort of function whose Laplace transform is f, and therefore the unique function whose Laplace transform is f, if we care about the function only being defined of the positive reals. Now, I guess I don't have to say anything about whether any function has a Laplace inverse. So in other words, is the image of the Laplace transform every single function? Well, almost certainly no. But in particular for the functions that we care about that are rational functions, then yes, every rational function has a Laplace inverse. That we can do. So here are some examples. Did I erase anything here? I know. I went to her. So I have three examples. Let's say we take the inverse Laplace transform of 4 over s squared plus 16. So do we remember what function this is going to be?
Yes, it's like sine of 4t.
Yeah, that's right. Sine is the better function. It doesn't give the linear term. So again, by convention, this when we're taking a inverse Laplace transform, this is going to be a function of s, and the result is going to be a function of t. And when we're taking the Laplace transform, we're taking the Laplace transform of a function of t, and the result is going to be a function of s. So that's going to be our consistent notational convention for what these variables mean. In other words, there's sort of an implicit t here. But we don't have to write it because we've agreed that that's what the meaning of t is. Now, this is going to be a bit more interesting. The Laplace transform, inverse Laplace transform of 6 divided by s plus 2 to the 4th power. So what's the Laplace transform of t cubed? I guess I want to write this in blue. Go ahead.
Minus 1 to the n time. Oh, okay. So minus 6 over.
You're not going to get a sign. It's just n factorial. The two signs cancel each other out. So, and then divided by what?
S cubed?
Yeah, s to the 4th, it increases by 1. Because if you do the first power, then it's going to be 1 over s. And if you do the third power, it's going to be 1 over s to the 4th. Yeah, so this looks exactly like what we have, except there's a shift. So we want to do an inverse shift. Well, how does it work? Well, if we have the Laplace transform of, I guess, the inverse Laplace transform of f of s, let's say s minus a, then whatever function this is, its Laplace transform is, okay, wait, how do I say this? So if you consider the inverse Laplace transform of f, and then you multiply it by e to the at, because this is now going to be a function of t, and then you take the Laplace transform of this, then what you get as a result is it's going to be the Laplace transform of the inverse Laplace transform of f, except you're going to evaluate it at, so this is the Laplace transform of something, so you'd evaluate it at s minus a. Now, it should follow that this is the Laplace transform of, well, okay, so the Laplace transform of the minus Laplace transform is, they cancel each other out. So this is just f of s minus a. There we go. Okay, I got it. So as a corollary of this, if we take the inverse Laplace transform of both sides, well, then they cancel each other out again. And so we get e to the at times the inverse Laplace transform of f is equal to the inverse Laplace transform of f of s minus a. So therefore, if we have a function and we have s plus 2, and we have an inverse Laplace transform, what we can do is, well, so there's a plus 2, so the relevant exponential is going to be e to the minus 2, and then this is going to be a function of t, right? That's the relevance thing. And then it's going to be Laplace inverse of, then we're going to do the shift, 6 over s to the 4th. And we calculated what that was. That was going to be t cubed. I guess conventionally I'd write the polynomial first. So yeah, we got that. We got that problem. That's good. So basically, if you want to shift, you bring the exponential out of the inverse transform. And this looks a lot more like the exponential shift theorem. So this is like basically literally the exponential shift theorem. Okay, except the sign changes, whereas in the exponential shift theorem, the sign didn't change. And there's no exponential multiplication here. It's just, so it's not the exponential shift theorem. It's not. But it's a bit like it. It's not any more like the exponential shift theorem than the last one was. Okay, any questions about that? So this is this was a very important calculation. We're going to be doing this a lot.
Then the only case which we didn't consider is if there's like an s on top.
Yeah, that's good. And that's going to be the next example. Although, by the way, we sort of haven't considered literally every single case. We're going to have to do partial fractions in general, but also you might sort of have, yeah, you know what, let's do that. So yeah, sure. What if you have something like s plus 1 divided by s squared? I'm just trying to actually ask myself, have we literally covered every single case? I might think we actually might have literally covered every single case. Yeah, this might be fully general. You might be right.
Is it linear? But is the Laplace inverse Laplace thing linear?
Thank you. The inverse Laplace transform. So if we have L inverse, let's say, of f equals f, and L inverse of g equals g, then we have that L of f equals f and L of g equals g. Now, if we consider L of f plus lambda g, that's going to equal f plus lambda g. Therefore, if we consider the inverse Laplace transform of f plus lambda g, then that's defined to be any function whose Laplace transform is this, right? And what's the function whose Laplace transform is this? It's f plus lambda g. Maybe I shouldn't have written this in the corner because it's an important thing. You know what? I'm going to do some space accounting. I guess I did it between examples. I could have done it at the end as well. Nope. So let's prove linearity. This shows L inverse linear. Excellent suggestion. Great. Okay. Now, okay, so if we look at this, so if we do, I guess you don't even have to do b squared minus 4ac. Sort of, if you have this 2s, how would you complete the square? It's sort of clear that it's a sum of squares. So if I'm writing s squared plus 2s, then what do I want here in order to factor it?
S plus 1 squared plus 4.
Good. And so that's clearly a sum of squares. So that's going to be the case. If this were not a sum of squares, then what we'd actually do is we just factor the bottom, and then we'd split it into two linear terms. But this is going to be an irreducible quadratic where we have to solve, complete the square. So now we want to shift this. It's s plus 1. So the relevant factor is going to be e to the negative t, right? And then it's going to be the inverse Laplace transform of, well, so s plus 1 gets replaced with s. And which one is this?
It's cosine
Of
t.
2t. Exactly. Okay, so that finishes the set of examples. Yeah, so I think you're right in that we've actually covered all of our bases. This is going to let us do pretty general partial fractions. So great. The examples that I do would sort of, they'd be very long examples. Now I have a table of Laplace transforms that I should write out. But I think that I'm going to write it out next lecture because it's going to be directly relevant to next lecture. So I'll write out the table at the start of next time. And then I will send you an email. I'll do this right now. I'll send you an email with both of the notes from the last two lectures. Actually, no, that's not true. Well, if I don't do it now, then I'll do it later. If I want to send the video, then I have to wait for like half an hour for Zoom to process the video. So I'll try as soon as the video is processed to send you. I need to do the last two lectures, so you haven't gotten the last one either. And then remember, we have a midterm on the weekends. I still need to write that. From Saturday at noon until Monday at noon. So it goes on until Monday for a bit. And it's not like actually the questions don't require 2 days to do it. So if you have 1 day combined in that 2 day period, then you should be fine. Okay. Any questions?
Yes, I have one.
Mhm.
About the L minus 1 F plus lambda G, why the result is uppercase G rather than small g?
Yeah, that's obviously a typo. Powering my tablet back on. Good catch. Okay, come on. Tablet. It's warming up again. No. Do the thing. Don't do the lagging thing. I think when I turn it off, it's already warmed up because you can see that sort of my cursor is moving very jaggedly. Because how it works is that there are induction coils, and then this pen, it doesn't have any power in it. And the coolest thing is that this pen has buttons. And the buttons work without any electricity. They sort of move something closer to the tip, and then sort of the induction field can tell from the tip if the tip is located on it. So like an Apple, you have a stylus that actually has a battery in it. But on this one, there's no battery. And this app, if you write light or heavy, actually, you can see that there's a difference in thickness. So I do get the difference in thickness, even without having this pen have any power. And that's really amazing. So that's Wacom technology. Okay, yeah, it's G.
And in the email with all the or with the lecture videos from the last 2 lectures, can you include like the list of all the topics we've covered?
Thank you. I will do that. Sure. Yes.
Thank you.
Good. Okay, thanks for the reminder. So see you tomorrow.